So hello everyone, my registration number is 19BC1676 and my name is Aditya Pokria. So today what we are going to talk about RSA crypto system. So let's first of all let's talk about introduction. So basically RSA full form is Rivest, Shamir and Adleman. Of basically these are the names who made in this one RSA crypto system. They are basically from MIT and they did this work in 1977 and they are best known and widely used public key scheme, and it is based on exponentiation in a finite Gaussian field over integers modular prime. Exponentiation takes, as you can see, this is the digit, you can see operations. It uses large integers, for example 1024 bits, and it is security due to cost of factoring large numbers. Its factorization takes this much, as you can see on my screen. So let's talk about the key generation. Basically, the RSA involves a public key and a private key. And these are the two keys which we are going to talk about. And the public key can be known to everyone and is used for encrypting the messages. Messages encrypted with the public key can only be decrypted using the private key. The keys for the RSA algorithm are generated the following way. Let me show you. So yeah, this is the RSA key setup. Each user generates a public private key pair, not a single one by one pair. So selecting two large primes at random P and Q, computing their system modulus n equal to P dot Q, as you can see, this one is the formula. So selecting at random the encryption key E, basically E can be anything, and you can see which has to be greater than this much and less than this much. So by after this, what we do, we publish their public encryption key and keep secret private key decryption key. So yeah, basically the step one is, for security purposes, the integer p and q should be chosen uniformly at random and should be of similar bit length. Prime integers can be efficiently found using a primary test. In step 2, choosing E with a small having weight results in more efficient encryption. Small public exponents such as E equal to 3 could be potentially lead to greater security risk. We will talk about this one later. So the public key consists of the modulus n and the public or encryption exponent E. The private key consists of the modulus n and the private exponent d, which must be kept secret. So yeah, next question is, what's basically the RSA use? So for to encrypt the message M, the sender obtains public key of recipient, you can see, which computes this one C equal to m raised to power e module n, where m is greater than 0 and less than n. So for decrypting the ciphertext, C, the owner uses the private key as we talked about earlier. So as you can see, what the cipher is C is doing, it's computing m equal to c raised to power d modulo n. Note that the message m must be smaller than the modulus n. Block if needed. So why RSA works? Because it's basically because of Euler's theorem. As you can see, this is the Euler's theorem formula. This one, as you can see, carefully chosen E and D to be inverses module phi n, and this one you can see c raised to power d equal to m raised to power e t. This one is basically are the formulas of the Euler's theorem. So now let's look at the RSA example. First, what you have to do, you have to choose the primes and then compute n equal to pq, then compute them, and then after select the GCD and then choose equal to 7. Basically we have to choose, determine that d equal to 1. As you can see, this d is less than 160, where we are getting a value of d equal to 23. And then after publish the public key, where is ku equal to 7187,187. Keep secret private key kr equal to 231711. Yeah, so after that, sample RSA encryption decryption is, given message m equal to 88, encryption c equal to 887 modulus 187, which results into 11. And in the decryption, m equal to 1123 modulus 187 equal to 88. So after the, yeah, I'm sorry guys, basically I made a mistake. Yeah, it was actually the 88 raised to power 7 in encryption, and in decryption it was 11 raised to power 23. After that we are getting this one. This one is the accurate result, not this one. Not this one. This one. Yeah, so let's now talk about exponential. It can be used the square and multiply algorithm. It is a fast, efficient algorithm for exponentiation. Concept is based on repeatedly squaring base and multiplying in the ones that are needed to compute the results. Look at binary representation of the exponents. It only takes O log 2 and multiplies for number n. Example, as you can see, this one is the example, and next one is also the example. Now let's move to the next slide. Yeah, now let's talk about the RSA key generation. Users of RSA must determine two primes at a random PQ, select either E or D, compute the other. Primes PQ must not be easily derived from modulus, which is basically I told you right now earlier, but it's in detail. So primes PQ must not be easily derived from modulus n equal to PQ. It means must be sufficiently large. Typically guess and use probabilistic test. Exponents ED are inverses. So use inverse algorithm to compute the other. Now let's talk about the factoring algorithm. A method tradition is a trial division. We will divide successfully by 2, 3, 5, 7, 11. These are basically, as you can see, these are basically the prime numbers which you are talking about. This method is just effective for the number up to this much digit. You can see basically how much this one is 10 lakh. Not with a large number, because the worst case time to factor a composite n is the square root of n divisions. Now we will consider three other methods. Express n as the difference of two squares, algorithm D format, and express n as the sum of two squares in different ways. Finally, Pollard's row method. So yeah, these are the three methods which we were talking about. First one is algorithm of Fermat. Second one is algorithm of Euler, and the last one Pollard's row method. We are basically going to talk about the Pollard's row method, not the above one. We are going to talk about that, but only the basic theorem. Yeah. So in algorithm of format, this method is based on the formula of difference of two squares. As you can see, x raised to power 2 minus y raised to power 2 is equal to x minus y into x plus y. Now, this second one, algorithm of Euler. The idea of this method is that if we can express number n as the sum of two squares in two different ways, we can factor n. We will talk about the condition of such expression. Now we suppose that n can be displayed as two sum of two squares. Yeah, now finally let's talk about the Pollard's row method. Let's say p is one of two factors of n. If you start picking up numbers at random, keeping your numbers greater or equal to 0 and strictly less than n, then only time you will get A equivalent to B modulus n is when A and B are identical. However, since P is smaller than n, there is a good chance then that A is equivalent to B modulus P, sometimes when A and B are not identical. As you can see what I said earlier, I said that they can be A and B are identical, but later there is a good chance that sometimes A and B are, when A and B are not identical, we can get equivalent. So A is equivalent to B modulus P means A minus B is a multiple of P. We also know that the N is multiple of P. So to find P, all we have to do is to compute GCD. GCD, which we have got A minus B comma N. And where A minus B is a multiple of B, as I told you. So this principle of Pollard's row method is to pick a random number A, pick another random number B, see if the greatest common divisor of A minus B and N is greater than 1. If not, pick another random number C. We are going to do this again and again. So now check the greatest common divisor of c minus b and n. If that is not the greatest, then 1. Check the greatest common divisor of c minus a and n. If that doesn't work, pick another random number d. Check d minus c, d minus b, and d minus a. Continue in this way until you find a factor. This is going to take a lot of hard work, but you have to do if you have to find a factor. So now, factoring problem. What's a factoring problem? Mathematical approach takes three forms. First one is factor n equal to pq, hence find a phi n and then d. The second one determine phi n directly and find d. And the last one find d directly. So currently believe all equivalent to factoring have seen slow improvements over the years as of August 1999. Best is 130 decimal digits, 512 bits with GNFS. Biggest improvement comes from improved algorithm. CF, quadratic CF to generalized number field CF, bearing dramatic breakthrough. 1024 plus bit RSA secure. Ensure PQ of similar size and matching other constraints. So now let's talk about the RSA security. Three approaches to attacking RSA which takes place. First one is brute force key search, infeasible given size of numbers. Mathematical attacks based on difficulty of computing phi n by factoring modulus n. And the last one is timing attacks on running of decryption. So yeah, brute force key search, which is infeasible given size of numbers. If the RSA key is too short, the modulus can be factored by just using a brute force. A 256-bit modulus can be factored in a couple of minutes. A 512-bit modulus takes several weeks on modern consumer hardware. Factoring 1024 bits keys is definitely not possible in a reasonable time with reasonable means, but may be possible for well-equipped attackers. 2048-bit is secured against a brute force factoring. As some students may be observing this, that the number of bits we are increasing, the number of brute force attacking probability is getting less. So basically, if the key is large, then the brute force will not take place. Now, the second one, mathematical attacks, which is based on difficulty of computing phi n by factoring modulus n. One attack on RSA is to try to factor the modulus n. If we could factor n, we could calculate n by using the extended Euclidean algorithm and determine d would work. The problem is that, like the other brute force technique, it's not practical actually. Yeah, so now let's talk about the timing attacks. It was basically developed in mid 1990s, which was exploit timing variation in operations, example multiplying by small versus large numbers, or IFs varying which instructions executed, infer operand size based on time taken, infer operand size based on time taken, RSA exploits time taken in exponentiations, countermeasures use constant exponentiation time and random delays, and blind values used in calculations. Now let's talk about the against attack. Basically, there are three types of against attack. First one is Chinese remainder theorem. The second one is padding scheme, and the third one is padding method. Yeah. So as we know, the generation of keys RSA is the series of operations modulus. The more keys length, the more time consuming on computer. More important, RSA using CRT can be saved from timing attack because we don't compute directly modulus D, the private key, which is the private key, but the modulus of factors. We can see it so far in this report. The Chinese have the genius idea, which is we can express the modulus of a number as the modulus of its factors. So we won't compute the modulus directly with D. It will may prevent the timing attack. Let n equal to pq denote a RSA modulus, EA a public exponent, and D the corresponding private exponent. So that let CRT xy mod n denote the number set such that note that this number is uniquely which is determined modulus 1 and modulus pxz you can see. So Speed up the RSA generation of keys with CRT. With the help of from CRT, we can speed up the decryption of RSA as follows. As a first idea, we can compute the result mode P and Q separately. That is the that is to merge the results of mode P and Q. This will require twice as many operations as we need to compute two exponentiations. However, as partial results need only to be calculated modulo P and modulo Q respectively, those operations are done with the numbers of only half as many bits. Hence, each multiplication costs only a fourth of what it cost for full size numbers. As CRT is almost for free, we gain a factor about 2 in a running time. Now let's talk about the padding scheme. When used in practice, RSA is generally combined with some padding scheme. The goal of the padding scheme is to prevent a number of attacks work against RSA without padding. When encrypting the low encryption exponents, example equal to 3, small values of the m, which is m is less than n raised to power 1 by e. The result of me is strictly less than modulus n. In this case, ciphertext can be easily decrypted by taking the eth root of the ciphertext over the integers. Because RSA encryption is a deterministic encryption algorithm that has no random component, an attacker can successfully launch a chosen plain text attack against the crypto system by encrypting likely plain text under the public key and test if they are equal to the ciphertext. A crypto system is called semantically secure if an attacker cannot distinguish two encryptions from each other. Even if the attacker knows or has chosen the corresponding plaintext as described, RSA without padding is not semantically secure. RSA has the property that the product of two ciphertexts is equal to the encryption of the product of the respective plaintext, that is m1 raised to power e dot m2 raised to power e equal to m1 m2 raised to power e. Because of the multiplicative property, chosen ciphertext is possible. Example, an attacker who wants to know the decryption of a ciphertext C equal to n raised to power e module n may ask the holder of the private key to decrypt an unsuspicious looking ciphertext, which is this C dash, for some value R chosen by the attacker. Because of the multiplicative property, C dash is the inscription of MR mod n. Hence, if the attacker is successful with the attack, he will learn MR mod n, from which he can derive the message M by multiplying MR with the modular inverse of R modulo n. To avoid this problem, practical RSA implementations typically embed some form of structure randomized padding into the value M. Before encrypting it, this padding ensures that M does not fall into the range of insecure plaintext that a given message, once padded, will encrypt to one of a large number of different possible ciphertexts. As single set 1 bit is added to the message, and then as many reset 0 bit as required are added. The number of reset 0 bits added will depend on the block boundary to which the message needs to be extended. In bit terms, this is 100.0. In hex byte terms, you can say this is, and in hex byte terms, this is 8000. This method can be used to pad messages which are any number of bits long, not necessarily a whole number of bytes long. Padding is in a whole bytes octets. The value of each added byte is the number of bytes that are added, that is n bytes each of value n are added. The number of bytes added will depend on the block boundary to which message needs to be extended. The paddle will be one of, as you can see, this is 01, 02, 02, 03, 03, 03, etc. This can be this one. So now, let's talk about the conclusion. By studying the cryptography algorithm RSA, I've learned many famous theorems such as Euler's theorem, Fermat's theorem, Chinese remainder theorem, and their application in RSA. The concepts congruence relation theorems, Euler's Gaussian functions, modular multiplicative inverse modular exponential, padding scheme, the extended Euclidean algorithm for resolving the modulo multiplicative inverse in order to finding the private key, square and multiplying algorithm for modular expressions, exponentiation. With mastering the principle of RSA, we find out the vulnerabilities of it, and we also studied how to defend the RSA against an experienced attacker. That's the padding scheme. Of course, we have many other types of attacks like factorizing directly and which is PQ or timing attack, but this is not the part. And we have a Actually, for our conclusion, the system using RSA is not always protected in spite of its strength. The timing attack showed us the attacker can break a system without knowing the algorithm of encryption decryption. As we can see about the attackers, we have to know the private key D and then compute the modulus to obtain the message. After that, the research has responded this type of attack by using Chinese remainder theorem. Then again, we have another type of attack called fault attack. In fact, the fault compute X and Y1 and 2 can be used for descripting P or Q. As you can see, this one is basically the fault attack which we were talking about. By computing GCD Z1 minus Z, we will have P, the first divisor. Finally, only one regret is that we could not implement a timing attack and OpenSL as we planned the proof of all theorems. But also the implementations of the algorithm took us too much time. Thank you, and hope you like it, and thank you very much.